Well, good morning, everyone. We're going to work on arc length again today. Hopefully we'll get it finished today and then we can start improper integrals next time. I think we're going to have an issue with the sections we'll be able to do, because I just noticed, I should have paid attention, but I didn't, that the 11th is a holiday, which I believe is a Wednesday. And so that's another day we're going to miss. So I'll adjust the homework accordingly. I don't think there's any point in me rushing through stuff just because it had to be finished by Friday. I don't think that's a good thing to do. So we are going to look at basically arc length questions where at the end, not at the beginning, but at the end you're going to get square roots that look like this and square roots that look like that. And we're going to focus on the algebra of perfect squares, which is what these questions are in particular. So not doing any integration right now. I'm just going to focus on how you get things to look like this. Well, they're called perfect squares. Now, one of the things that will be true is that there will always be three terms. So if you're doing an arc length question and inside the square root there are three things, three terms, you are looking at a perfect square, even if it doesn't look like it. The only change to that rule is if the question says, oh, give the answer to 2 decimal places, then you would just plug the horrible mess, whatever it is, into your calculator and it doesn't matter. But if it doesn't mention use your calculator 2 decimal place kind of thing, and there's three guys inside the square root, it's going to be a perfect square. Now, some perfect squares are very easy. So can you imagine that was the quadratic inside the square root? That factors as two terms that are the same, and that's what I mean by a perfect square. Okay, so when I say perfect squares, I just mean a three-term expression that can be written as something squared. But not all three terms expressions are equal. Some are much more difficult to recognize as perfect squares. This guy is also a perfect square. But what is that perfect square? Well, what goes here?
X squared.
X squared.
Great. And what goes here?
Plus 3.
Now, if you don't believe that, file that out. It works, right? Now, they're going to be weirder than that. That's not anywhere near as weird as some of the ones that are still perfect squares. They're just not going to even vaguely look like them. Here's one. Just making sure I'm telling you the truth here. There you go. 1/4 x to the 6, take away a half, take away 1/4 x to the -6. That is a perfect square. Doesn't look like it. Certainly doesn't have any shape to it that makes you think that. But it does have three terms, so it has to be. So whenever you're doing one of these arc lengths and the thing inside the square root ends up as three terms, you're going to say it's a perfect square. Make sure you write them in order and then do this trick. You only care what the first and last term is. The guy in the middle will sort itself out. The guy and, oops. The guy in the middle will sort himself out. One quarter gets you half. X to the 6 gets you x cubed. 1 quarter gets you a half. And x to that gets you that. And you got that guy. Now you FOIL that darn thing out and you will get this fella. So there is a way of figuring out what the perfect square is. You look at the first term and you take its square root. You look at this last term and you take its square root. So quarters get you halves, right? Square root of x to the 6 is basically, isn't it, half its power? So that's an x cubed. And negative 6 half its power is negative 3, and the square root of that guy is this, right? I had to play about with the middle and the signs to make this work, but don't worry about the middle term. If you do these correct, the middle term will just come out, you know, as part of the process. So I don't care if that middle term looks really ugly. I don't even care what it is. As long as I do these correct, the middle term will work, because these questions will be perfect squares, right? So we know that they have to work. We feel okay with that? Do you want another example converted into a perfect square just to get a feel for it? You want another one? Your choice.
Could you show us real quick how that 1/2 does actually come out?
Oh, this way? Okay. So what I'm going to have to do is take this guy and multiply it by himself, right? Well, while I'm at it, let me show you the whole thing working then. If you do that guy times that guy, 1/2 x cubed times itself gets you 1 quarter x to the 6. That matches, right? Now that's the f. If you do the outside, 1/2 x cubed times 1/2 x to negative 3. Well, the two halves combine to give me a quarter. What does x cubed times x to the negative 3 look like?
Should be 1, right?
Right, x to the 0, which is 1. So you get a quarter. And if you go the other way, you get another quarter. And then the last guy, you get 1/2 times 1/2. Oh, and you see the plus 1/2? It works. We're good? Right. So let's pick some that do that. Who knows? There are so many in here. They're all over the place. I'm trying to find one that comes out without too much hassle. Perfect square. Okay, this is question 5, or at least one like it. Y is x cubed over 3. Yeah. Plus 1 over 4x. And it's going to be the arc length from x equals 1 to 3. So I'll find the derivative. Well, actually, I won't yet. I will write this guy in that format. I haven't taken the derivative yet. This guy is a third, which is kind of obvious. This one is not so obvious, but why did I turn this guy into that guy before I differentiated? Why not just leave it like that, I guess?
So it's easier to deal with the x.
Yeah, because I'm going to have to use the power rule, right? And so x to the -1 makes sense. No, that is not a log. That's what you get if you integrate. See, you've got two hats on right now. Right now, we've got the differentiation hat on. Later on, we'll have an integration hat on, right? Sometimes you're differentiating things. Other times you're finding antiderivatives. So power rule, differentiation. Multiply by the power, reduce it by 1. Multiply the power and reduce it by 1. So there is my derivative. So I now have to square it, which means I'm going to have to take this guy and I'm going to have to multiply him by itself, which means we're going to do FOIL. There's the first one, the F. X squared times x squared, not a big deal, x to the 4. Now the weird one. X squared, I guess I could do it up here, x squared times -1/4 x to -2. What on earth does that become?
-1/4.
Great. Won't the 2 and the -2 get you x to the 0, but x to the 0 is 1, so you just get left with the number -1/4. Now I'm going to speed up the second one. That's the same calculation, just in the reverse order. And now we've got the last guy. Well, -1/4 x to -2 times itself. Well, negative and a negative gets me a plus. And x to the -2 times x to -2 gets me x to -4. And so now we're looking at x to the 4, subtract a half, plus 1 x to -4. And that's what that guy looks like. Now I'm taking this really slowly, hopefully, slowly enough. Shouldn't we now add 1? And we get x to the 4 plus a half plus 1/16 x to -4. That's the guy that's going to go inside the square root. He's got 3 terms. He has to be a perfect square because that's the only ones that are going to work. And so I need to know what perfect square. And remember the trick. You only care what the first and last term does. The middle one will sort itself out. So what will I get from the x to the 4? What will that become?
X squared.
Right, so you half the power. That's how you get the square root of something. Won't this get you 1/4 x to the half power? -2 in this case. I'm not going to do it this time, but can you trust me? If you follow this out, it works. It's a perfect square. Which means we can now essentially complete the question. The arc length is going to be the integral from 1 to 3, the square root of 1 plus the derivative squared, and I'm using that version of the formula rather than this one because we were using y dash. That's the only difference. And that's the integral from 1 to 3 of the square root of x squared plus 1/4 x to -2 squared. But perfect squares play really well with square roots because don't they essentially cancel each other out? And so we now have an integral that doesn't have a really weird and ugly square root that we need to deal with. don't we basically just have a power rule integral? Agreed? Now, this one I'm actually going to take to the end. Normally I would dot, dot, dot this one, but I kind of want this question to be your template for all the perfect square questions, right? So you get an idea of what you would do as you go through the process. So according to the power rule, you add 1 to the power, right? And divide by the new power. If you add 1 to this guy, you get -1. And if you divide by that power, you get this. And you evaluate it at x equals 1 to x equals 3. But I would rewrite that. Okay. And you might think, why bother? Remember, we have to write this answer down in its nicest exact form, right? No decimals anywhere. If I left it as x to the -1, wouldn't I be writing things like 1/4 3 to the power of -1, which should jar your brain, right? It doesn't feel right. Would you agree that this is the same as that? But when I put the numbers in, we're going to get much nicer numbers. It's going to be 1/3 3 cubed, take away 1 lot of 4 times 3, subtract essentially 1/3, take away 1/4. So that's going to be 9, subtract a 12th, subtract 1/3, subtract a negative, add 1/4. And that's what calculators are for. So here goes. 9, subtract 1/12, subtract 1/3, add 1/4. Hit the math button, menu choice 1, turn it into a fraction. We're done. Now, as you get more proficient at this, can you probably guess that you're going to skip some lines? And you're going to say, I don't really need to do this line. I can do 2 lines at once and get to the answer. And that's great. You know, when you feel comfortable, you should try and do that. But at least I think I have written every line I can think of, and probably some that I didn't need to. But do you feel comfortable about each step? It hasn't jumped. God, how did you get from line 7 to 8? Okay, so that's our first example of a arc length question that involved a perfect square. Through some of my notes here. I think I had another one set up from the last class, so I'd like to do that if I can. No, evidently, maybe. I've got a couple more here. Yeah, a little messier. This one. So this is like question 8. X squared log x. And we're going to get an arc length from 1 to 4. Get that out of the way, it's distracting me now. Okay. Differentiate, multiply by the power, reduce the power by 1. Agreed? What's the derivative of log x? Derivative of log x.
1 over x.
Right. And I am going to change that guy. I'm going to call 1 over x, x to the -1. And one of the reasons I want to do that is to make the foiling a little bit cleaner, right? So I'm going to square it and add 1. So let's go 1 add this guy squared, right? 1 add this guy times this guy. For instance, you might not bother to write that line. Can you probably write this line instead? Okay. Just noticed, lost a little exit. 1/2 x times itself is 1/4 x squared. What will 1/2 x times negative 1/2 x to the negative 1 get me? So I'll write that up here. What would 1/2 x times negative 1/2 x to negative 1? What will that get me? It's happened twice. I think it's happened twice.
Negative 1/4.
Have you noticed that you end up with a number in the middle, right? So what do we get? Well, we get negative 1/4. If you go the other way, you get negative 1/4. And if you finish off, two negatives make a plus, and you get 1/4 x to negative 1. That eventually becomes this fella. Negative 1/2 add 1 gets you plus 1/2. And then you finish with, that's a 2 there.
Shouldn't you get, yeah.
So I know that that's the guy that's going to go in the square root, but I also know it's got 3 terms. So that means it's a perfect square. If it's got 2 terms, it's not a perfect square, it's something else, right? But it's got 3, so it is a perfect square. What will this guy get me? What will 1/2 x squared get me? Well, almost said the answer there. 1/4 x squared.
1/2 x.
And what will this ugly guy get me? Any takers? 1/4 x to negative 2. What will you get if you take its pieces and square root them, essentially?
1/2 x to the negative 1, positive.
Agreed? Right. Now, you know that guy's going to go inside this square root, right? So let's see what the arc length looks like. It's integral from 1 to 4. The square root of 1/2 x add 1/2 x to negative 1 squared. We kind of like that because perfect squares in these questions come out really nicely, don't they? Because they cancel out with the square root. And so what we have is the integral from 1 to 4 of 1/2 x plus 1/2. And I'm not going to call it x to negative 1. I'm not going to change it. And instead of calling it x to negative 1, I'm going to call it 1/x. Have you any idea why I bothered to do that? Why I didn't just call it x to negative 1? Why am I changing the way it looks?
You need to log it.
Yeah. And so when you find the antiderivative, isn't it better to realize this is a log? If you left it as x to negative 1, wouldn't you perhaps try and do the power rule on it? And you know that's not going to end well, right? Right? You end up with a 0, and divide by 0 is not good news. So this is add 1 to the power, divide by the new power, and this gets you half log x. And at this point, I think it's time for ... Looking good? Give you a few seconds. Any questions about that? Because I was a little bit more, quicker and maybe not wrote every line I could possibly think of in it. Feel comfortable about what we did? That one out the way. Question 6, like it. There are two versions of the arc length. We've been using mostly this, but can't you also do curves that go vertically downwards, in which case x is a function of y? Right? Me personally, I like to call this guy g of y. And I think it's just psychological. We use x as a variable so much that if you leave it in this form, you can kind of get distracted. So isn't this the equivalent of that? So I'm just trying to make it easier in my brain. Now, if I'm going to differentiate this guy, and I want to write it in a format that's going to make it easier to do, would you agree that I have to convert it to look like this guy so I can use the power rule? So you're happy about the y over 4 gets you an eighth, and that the 1 over 4y squared gets you a quarter y to negative 2. Do you know one of the most common algebraic mistakes people make in going from here to here? They don't call it a quarter y to the negative 2. They call it 4y to the negative 2. I still see that from time to time. It's not right, okay? It's a mistake, but I can kind of understand where their thought process. Don't you just see that? And so you think that the 4 and the y squared are like brother and sister, right? They're stuck together. But technically, isn't that a quarter? You see, and that's what it really is. Now, you're going to differentiate. Multiply by the power, reduce it by 1. Multiply by the power, reduce it by 1. We're then going to square it and add 1. Looking good? Kind of has the same flow as the other two. I'm going to skip a line here, maybe 2 lines. Are you happy about doing the foiling and it ends up looking like those 4 guys? You can fill in the missing line if you wish, but that's what we get. Which means that we are now going to get that guy. Oh, you okay with that? The 2 quarters and a half and all goes together. Now that's going to become a perfect square. Okay, I think 3rd time we've done this, so each time it gets a little bit easier, I hope. One quarter y to the 6. What the heck does 1/4 y to the 6 get you?
One half y to the 3rd.
And won't this guy get you 1/2 y to the negative 3? And we were just quite happy in saying the half will sort itself out, because it always does. Here's a little trick that isn't true all the time, but it's true often enough to be noticed. If you look at g dashed of y, and you look at this guy here, do you notice that they're almost identical? One's negative and the other's plus. If you go back and look at the other two examples, that same thing is true. That the derivative will look very much like the guy inside the squares. The difference will be that they'll be added instead of subtracted. That's a very common feature. It's not just a coincidence. It does happen a lot. It especially happens when we're talking about y cubes and y squareds and y to the -3s and things like that. It happens a lot in those situations. And it's a good kind of halfway house check that you're on the right road. Right. Now, to continue with this question, the integral for the arc length is from 1 to 2 of the square root of 1 plus the derivative squared with respect to y. And that's the integral from 1 to 2 of 1/2 y cubed plus 1/2 y to the -3 squared, all inside the big square root. And they cancel out. And aren't you just left with a power rule integral? Right, nothing, none too weird. Right, and be careful with that guy. Will you remember to turn them into whatever it is? I don't know what the numbers is, whatever. Yeah, whatever it turns into, will you make sure that you write it like this so that you get answers like a quarter and an eighth, and not answers like 1/2, 2 to the -3 or something, which isn't considered good form. So do the power rule and then make it look pretty. And after it's pretty, which basically means negative powers get turned into fractions. Once that's done, then you can plug y equals 2 and 1. Are we good? Now move on to the next example. I'm going to do a perfect square that looks nothing like those, a trig one. Oops, try that again, it's not an integral yet. Now, I said this is going to be a perfect square, but it's not going to be like the ones that we've just done, because trig, they have their own algebra, right? They have their own weird stuff that they do. So here goes. Oh, let's do dy by dx, just so I'm not using the same notation, right? I'm basically going to differentiate it. Do you recognize this as a chain rule question? It's a natural log of a secant, so it's a chain rule. So when you differentiate a natural log, you get 1 over the thing, and then don't you get the derivative of secant x? Okay, we are differentiation hat on. What is the derivative of secant x?
Secant 10.
Great. And actually, that's very good news. Because doesn't the derivative simplify just to tan x? Now I'm going to do 1 plus the derivative squared. Well, that's going to be 1 plus tan squared. And I said, that's a perfect square. And it is. Who is he?
Secant squared.
So, when you do trig, all bets are off. When you do trig things, right? So don't expect, foiling and all that kind of thing. More likely, you're going to have to deal with identities and stuff like that. Now, in this case, then, the arc length is the integral from 0 to pi upon 6 the square root of 1 plus the derivative squared dx. That becomes the integral from 0 to pi upon 6, the square root of secant squared x dx, which now becomes just the integral of secant x. If you don't know the integral of secant x, can't you go and look at the table of values, guy? But we did actually write that down somewhere. And somebody in the other class actually remembered it, which I was very impressed by. Can anybody remember what the integral of secant x is? I'll start it off for you. Natural log of,
The natural log of secant x plus tan x.
and I can tell that you were looking at it, right? Which is a good reason why you should have notes at your side, because you don't know what's going to appear, right? You know, especially when trig involved, who knows what weird integral is going to come out? Evaluated at 0 and pi upon 6. Well, okay, you're also going to have your unit circle handy, because don't you now need to find exact values for secant of pi upon 6 and tangent of pi upon 6? Right, because you aren't allowed to say 1.17, right? You're going to have to say root 2 over 2 or square root of 3 or something, right? Whatever it ends up being. All questions are exact answers unless the question says to 2 decimal places. So you can't write down decimals because you want to, right? It won't accept them. Kind of cool. Right. I want to finish with a really big, ugly question. I'm just trying to make sure I can find it. It's higher up than that. I don't know where it is. I found it. I really like this question. The guy, and I use the word guy to mean girl or man, was really clever. I don't know how he put this together. You know, if you just randomly pick a function, by the time you've differentiated it, squared it, and add 1, would you agree it's probably going to be an ugly mess that you can't make pretty, right? If you just randomly picked it. He picked this one. And it ends up being, oh, by the way, the answer I believe is from 0 to 1, but I'm not even going to worry about that. Let's just get the integral part done. You can plug in numbers later. Looking at that, does that look like it's going to end well? Doesn't that look like it's going to be some horrendously ugly answer? You're going to be amazed at what the final answer looks like, because it is going to look decidedly really ugly. It's also going to involve you dealing with algebra in a way that maybe you're not comfortable with, but you've got to get good at. So first thing I'm going to do is just rewrite the square root as a half power. Because I have to differentiate. And if you're going to differentiate, don't square roots have to be half powers, right? That's really what I'm doing. Now I'm going to do the derivative. I guess I'll call it y dash this time. This is a chain rule, and so is this. This is not too bad a chain rule, but it will throw some of you. You multiply by the power, and you reduce the power by 1. But it's a chain rule. Don't you finish with the derivative of x minus x squared? Great. Now, the derivative of x minus x squared is 1, take away 2x. That doesn't look good. Right, next fella. Does anybody remember what the derivative of an inverse sine function is? The derivative of an inverse sine function. Go for it.
I've got 1 over the square root of 1 minus x squared.
Right, so I want you to think of 1 over the square root of 1 minus x squared as not being an x anymore. Think of the x as a placeholder. So it's actually 1 over the square root of 1, whatever you give me, squared. So in this case, it's going to be 1 over the square root of 1, whatever you give me, squared, times the derivative of the square root of x. Oh, darn it, I should have turned him into x to the half, but I forgot to. Okay, what is the derivative of x to the half? Would you agree it's power rule? Can I call it that guy? And can I now call it that guy? Okay, so you're going to multiply by 1 over 2 square root of x. Pretty much as ugly as you thought it was going to be, right? So I am not going to square that guy yet. I want to make this guy as pretty as possible. Right? And I call that style points, that process. And the rules for style points are things like factor the heck out of it and make it look like the original. Right? So I'm going to take this term and I'm going to call it 1 minus 2x on the top. That 2 is going to come downstairs, and that negative a half is going to look like that. And this fella here, well, if you take a square root and square it, you get x. And then you're going to have a 2 square root of x, right? So far, so good. Right. Now, can I call half powers square roots? If you've got a square root of x and a square root of 1 minus x, aren't you allowed to multiply them together and make a single square root of them? And so if I multiply x by these two terms, I get 2 lots of x take away x squared. Have you noticed that what style points has allowed me to do is that it's now shown me that two things that didn't really look that much like each other are in fact the same fraction, at least as the denominator goes. Which means, can't I now just add the numerators? Great. If you add the numerator, you're now looking at this guy. Would you agree that ugly mess is beginning to look nicer? Is there anything else I could do? Because remember, factor the heck out of it and make it look like the original. Is there anything else I can do?
Factor 2 out the top.
Agreed. Which means that it can now be simplified down to that guy. Now, compared to what it used to look like, would you agree that's a much tighter looking thing? Right. Oh, and by the way, I've only differentiated. I haven't squared or added 1 yet. So let's do that. Actually, I'll do it in the next page. So I now know that y dashed is 1 take away x over the square root of x minus x squared. So if you want to square it and add 1, you go 1 plus this guy squared. Well, isn't that this guy over this guy? Which means that it's that guy over, oh, x take away x squared. Things looking good? Is there anything I can do to this bottom fraction that might help?
Factor out next.
Now you notice I didn't FOIL out the top. Can you see why I didn't bother? Because won't this cancel one of these? And now I'm looking at that guy. Any ideas what I could do next? Think style points and making things look pretty. Anything I can do with this?
Turn the one.
Well, you started, but then your voice disappeared, Javon.
Well, I was thinking that you could turn the 1 into an x.
Oh,
over
that's a
x.
different way of approaching it, but that works, so I will use it. Nothing wrong with that, Javon. That works perfectly. Wasn't the way I was going to do it, but that doesn't make it wrong. It just makes it different. Which means I can now combine these two. Oh, would you look at that? So we are now looking at the integral from 0 to 1 of the square root of 1 plus derivative squared, which is that, dx, which is the integral from 0 to 1 of 1 over the square root of x, which is integral from 0 to 1 of x to the negative a half. Now, considering what that ugly thing could have been, isn't it miraculous of what it actually was at the end? It ended up just being 1 over x. And inside the square root, 1 over x is easy to deal with. It's a fractional power. So power rule, all right, add 1 to the power, divide by the new power, plug in 1, plug in 0. I believe you get the answer 2. And you're good to go. Now, I've already seen this with the last class. I didn't actually know exactly what this was going to turn into with the last class, but now that I've seen it twice, I am still amazed. Is that not just a cool question? And it's kind of the lesson it's telling me is that algebra style points is your friend. If you can feel happy about dealing with weird fractional powers and squaring them and adding stuff and factoring and cancelling and all that whole repertoire of algebra, that it can actually help you to get the answer to some really ugly looking things. If I had left that guy like this and I said, okay, let's square it now, you're probably thinking about leaving the room, aren't you? I mean, God in Himmel, look at that. If I left it that way, can you imagine what that would look like squared? I mean, it would take up a piece of paper, right? And then good luck trying to make that nice, right? Would you agree? It would probably it would go south on you like nobody's business. So the moral of the story is style points. Make things look as nice as you can before you move on.